In this video, I will talk about numerical integration through the use of the so-called Simpson's methods. Now, Simpson's methods, well, they were named after their main inventor, Thomas Simpson, shown over here, who lived in the 18th century. But in some German texts, you would actually see the same methods being called Kepler's methods because they were actually also used already more than 100 years earlier than Simpson lived. They were already used by Johannes Kepler, the famous German mathematician and astronomer. Um, Now, what are Simpson's methods? Well, we've started this discussion on numerical integration with rectangle methods. And in rectangle methods, well, we uh, approximate f on the interval AB using a 0th degree polynomial with one corresponding evaluation point, whether that is the left-hand side for the left rectangle rule, the right-hand side of the interval for the right rectangle rule, or the middle for the midpoint rule. We saw the trapezoidal method where we use a first degree polynomial, so a line between two evaluation points, so the endpoints of the interval. And then finally, well, this kind of leads us directly to Simpson's methods. And in Simpson's methods, well, it's a natural extension of this idea. Not except now we approximate the function using a second degree polynomial, so that's a quadratic polynomial, and that will lead to what we call Simpson's 1/3 method. Why we call it like that will become clear. Um, and or a cubic polynomial, so a third degree polynomial, and that will lead to what we call Simpson's 3/8 method. And corresponding to this, well, we need 3 or 4 evaluation points dividing this interval AB into equal parts. That's Simpson's methods. So let's start out with the first of the two Simpson's methods, and that's the Simpson's 1/3 method. It's again a Newton-Cotes type method, which means that we approximate our function on the interval AB with a second degree polynomial. So for that we need 3 evaluation points or 3 collocation points as is also called. And what we do is we fit a second degree polynomial, so that's a quadratic polynomial or a parabola, here indicated by this light blue line. We fit a parabola to the function f of x, which in this case is clearly not a parabola. And we use these 3 points, so that's the left-hand side, the right-hand side, and the midpoint in between. So this parabola is determined by 3 coefficients, C0, C1, and C2, which are basically unknowns that we still have to determine based on f of x. Now, how do we determine these coefficients? Well, we can determine them in various ways, but the most natural way is obviously by requiring that the polynomial evaluated at these 3 points is equal to the function evaluated at those points. So we want that, well, the blue line and the black line coincide for x1, x2, and x3. And this leads us to, if we just plug in x1 into the polynomial, this is then the expression, so still C0, C1, and C2 are unknown. X1 is known because that is the value A, which is known beforehand. And here on the right-hand side, well, we want this to be equal to f evaluated at this point x1. So that's also something that we have to evaluate. So that's f evaluated at A, and that's also a number that we know or that we can easily compute. So this will give us 3 conditions, which basically is 3 equations in 3 unknowns. And this is a linear system of equations. So x1, x2, and x3 are known. So the fact that you have this square terms here doesn't make it nonlinear. This is linear in C0, C1, and C2. So you can solve this for C0, C1, and C2. And this is one of the methods that you can do in order to fit a polynomial to a function. If you want to study this in a bit more detail, you could look into chapter 7 of the textbook, which is not part of this course, but that's an entire chapter which discusses curve fitting and interpolation. So you could take a look at that. But for in this case, well, we just say we have here three equations, three unknowns, and we can solve this for C0, C1, and C2. What these actual values are, well, you could express them as a function of FA, FB. You can solve this system by hand, but I'm not going to do that because that's not the main point here. Again, you could look at chapter 7 if you'd like more details on that. And also I think in the textbook it's explained in a bit more detail, but that's really not the main point here. What is the main point is that, again, we approximate f of x on the interval AB by this polynomial function p of x, which we can determine. So we have now known C0, C1, and C2. We can simply plug that all in there. This will give us the integral of a polynomial function. That's something we can compute by hand. I'm not going to go into the details here because, again, they're not so important. But the outcome is the following. So the integration rule that we end up with is 1/3 times h times f evaluated at A plus f evaluated at B plus 4 times f evaluated at the midpoint between A and B. And we immediately see why this is called Simpson's 1/3 method, because here we have this factor 1/3 which pops up over here. That's why it's called the 1/3 method. Now, again, similar to trapezoidal or rectangle methods, we can try to increase the accuracy of Simpson's 1/3 method by not applying it in one step to the entire integration interval AB, but instead we can split up this interval into n subintervals, and in that sense we end up with the following. So we find that this integral can simply be rewritten as these subintegrals. And for each of these subintegrals, well, we apply Simpson's 1/3 method. So for this first interval, so I2, this first integral, let's say I2, applying Simpson's method here, well, that's f evaluate at the left-hand side, f evaluate at the right-hand side of the subinterval, and plus 4 times f evaluated at the midpoint between x1 and x3. So that's what we find here, and all of that multiplied with 1/3 h. We can do the same for this second blue area, which is I4. So that's fx evaluated integrated from x3 to x5. So that's simply, again, the left-hand side of the interval, the right-hand side of the interval, and 4 times the midpoint. And we can continue again to do this for each of the intervals that we come into. Now, we want to try and simplify this formula a bit, because we see that quite a lot of the function evaluations come back. So for example, here we see that f evaluated at x3 comes back in multiple terms. X2 is only singled out here, but you will see that many of these terms come back multiple times when evaluating this entire sum. So let's take a look at each of these evaluation points and check how many times they are added to this total sum over here. So, and we can do this by investigating each of these subintervals and then writing down here the coefficient that it is multiplied with in order to compute the area of that subinterval. And so we see here for this first part, so for I2, well, FA will be added to this total sum once. We have 4 times F at x2, and we have once F at x3. We repeat the same strategy for this I4 here, and then we see that this is actually this term over here. So we have 1 times f evaluated at x3, 4 times f evaluated at x4, and once again f evaluated at x5. And by if we continue to do this for all the intervals, well, and we sum up all the amount of times that we have to incorporate such a function evaluation here on top, we see that we have a recurring pattern. So we see that the endpoints of the total interval, they are added to the sum once. We see that all the even terms, so 2, 4, 6, 8, etc., they will be added to our sum 4 times, and all the odd terms that are not the endpoints, so 3, 5, 7, 9, etc., they will be added twice to this sum. So we can use this in order to simplify this long sum a little bit and simplify our notation a bit, which will also allow us to simplify this in implementation. So this is what this actually looks like. If we write this out a bit more concisely, so we just take a look at all of these terms over here. So the endpoints, well, they have a coefficient of 1, so we only add them once to this term. The even indices, so that's for I is 2, 4, 6, etc., they are added 4 times to this sum. The odd indices are added twice to this sum, and then this endpoint is added once again. So using this, well, you could implement this in MATLAB in a very similar way as we did for the trapezoidal rule or for the rectangle rule. You just have to take into account the even indices and odd indices in a slightly different manner. But that's fairly straightforward. Note, however, that this composite rule, well, it will only work if we have an even amount of total subintervals. So in this case, well, we have 12 intervals, so this nicely works out. We have 1, 2, 3, 4, 5, etc., 12. So we have in total 13 of these evaluation points, including the endpoints. However, if we were to add, let's say, one more point, then we would not easily be able to apply Simpson's rule to that, because for Simpson's rule, well, we always need 1 point in the middle, and if you don't have an even amount of intervals, well, or an even amount of evaluation points in total, then this won't work out. And you can easily check this by, for instance, drawing this out for, let's say, if you have 5 subintervals, then it simply won't work, and you won't be able to use Simpson's 1/3 method. Moving on to Simpson's 3/8 method. It's completely analogous to Simpson's 1/3 method, except now we fit a 3rd degree polynomial, so that's a cubic polynomial in this form over here, and we use 4 points. Those 4 points are evenly distributed among A, B. So we have them at A, we have it at B, and then we have it at A plus 1/3 times this width, and A plus 2/3 times the width of the interval. Now what is left for us to do? Again, we determine coefficients C0, C1, and C2, and C3 based on the fact that we want the polynomial to be equal to f of x at each of these points. And that's what we get. This gives us, again, 4 equations. So previously it was 3 equations, but here we have 4 equations, 4 unknowns. This is again a linear system that we can solve, and solve this for the coefficients. Also, again here, the details are not so important. The fact that you can write these C naught explicitly as combinations of FA, of FB, and of F at these middle points, that's also not very important. That's not the main point here, but the main point is that, again, we replace f of x on this interval by this polynomial for coefficients that we can determine if we want, and you could look them up what they are exactly, but that's not the main point. The main point is that, well, you come up with a polynomial. A polynomial is something you can integrate easily, and the end um, the end outcome that you find here will be that this is your Simpson's rule. So you have 3/8 times h times this sum of function evaluations that you have over there. Now, again, also for Simpson's 3/8 rule, we can come up with a composite rule. Because we use 3 points in this case, well, we do not integrate it only over 2 or over 3 points, but we have to integrate it from x1 to x4. So that means that we have here, for instance, for this first interval, we need this point, this point, this point, and this point, because through those 4 points, we can fit a cubic polynomial. And the same goes for here from x4 to x7. We can fit a cubic polynomial through this, and this point. So that means that, well, the Simpson's 3/8 method, the composite rule there, it will take 4 points in every step, in every subinterval, or let's say in every combination of subintervals there. And so that means we split up this integral from a to b into these subintervals, let's say. And for each of these subintervals, well, we apply Simpson's 3/8 rule. Simple as that. So for the first one, well, this comes down to, well, this is 3/8h. We have the left-hand side once, we have the right-hand side once, and then we have these 2 points in the middle, in between the left-hand side and the right-hand side of the area that we're computing here. Those have to be added 3 times, corresponding to what Simpson's 3/8 method tells us to do. And we do this simply again and again for each of the intervals. And similar to the composite Simpson's 1/3 method, we again count the contributions of each of these function evaluations between A and B, and we try to observe a pattern. And so indeed, we see here the endpoints, so the total endpoints A and B, they are added once to this entire sum. The multiples of 3. So multiples of 3. So that's here 3, 6, 9, 12. They are added 3 times to the sum. The multiples of 3 plus 1, so that's always 1 to the right of these multiples of 3. So those are always these edge points of these colored areas. They are added twice. And then the multiples of 3 minus 1, they are added again 3 times. So this means that we can translate this formula again into something which is a bit more compact by grouping the different kinds of terms that we have over there. And that's what happens here. So you see indeed that these endpoints, as indicated here in green, come by once. The multiples of 3 minus 1, so the indices to the left of multiples of 3 will be added 3 times, as indicated here by this deep red. The purple ones are multiples of 3, and the pink ones are multiples of 3 plus 1. And those are added twice. And so then you can see that this seems really to make sense. By grouping these terms, we can really make this summation a lot more concise, and it's much easier to implement something like that into MATLAB. Again, similar to Simpson's 1/3 method, which required the amount of subintervals or the amount of points there to be even. Here, it's required that this amount of subintervals, so where a subinterval is actually such an interval here, the total amount here has to be divisible by 3. Because if this is not the case, well, you can try this yourself, but it's also easy to see if it's not divisible by 3, you can never come up with a, um, a nice fitting stencil, let's say, in order to accommodate for all points by simply using the Simpson's 3/8 rule, because it will, in every step, it will add, let's say, 3 points to the total sum. And if this amount of subintervals is not divisible by 3, then this will not be possible. And the easiest way to check this for yourself is to try to write this out. For instance, if you have, let's say, 8 subintervals. So if you cut this entire thing, for instance, here at x9, that means that there will be 8 subintervals before it, and you try to use Simpson's method, you see that this doesn't really add up, because you could not use Simpson's method for only these 3 points. You would need an extra point, which would lead you to having 9 subintervals, which is divisible by 3. So I hope that makes some sense. So for both the Simpson's 1/3 rule and Simpson's 3/8 rule, we saw that there are some conditions on the total amount of subintervals that we can use. And this can be quite annoying, especially if you're not free to evaluate your function wherever you want. Now, this can be circumvented in a way. For instance, the situation can occur that n is odd and not divisible by 3. And that would mean that you cannot apply Simpson's 1/3 rule nor Simpson's 3/8 rule. So neither of those composite rules could be applied here. What you could do then is to combine both of these rules. So if n is odd, not divisible by 3, what we can do is, well, we use the 3/8 rule for either the first 3 or the last 3 subintervals. And then the remaining subintervals, so that will be n minus 3 that remain. Well, n was odd, so if you subtract an odd number, which is 3, from another odd number, you come up with an even number. So n minus 3 would be even, and on that we could use the composite 1/3 rule. Let's take a practical look at how this could look in practice. Here we have a function, f of x, which is divided into 13 subintervals. And you can count them, but I assure you that they are 13 subintervals. We could not use the composite 1/3 rule nor the composite 3/8 rule to do this integration. And you can try it, but it will not add up. You could not simply fit all of these nice individual Simpson's rules into those 13 subintervals. It will not work. What we can do, however, is use this strategy. So what we do is, well, we use the 3/8 rule for the first 3 subintervals. So that takes care of these ones in purple. And then what remains is, well, that will be n minus 3. So that's 10 subintervals. That's even. So we can simply use the 1/3 rule for the remaining 10 subintervals. And just writing this out here, so we see that in purple, that is the Simpson's 3/8 rule for these intervals. And then we can simply apply Simpson's 1/3 rule for the remaining intervals. So this is kind of a trick that you could use whenever you are faced with the situation that you cannot choose the amount of subintervals yourself, either when your function is tabulated or when you can only evaluate it at these specific points. So this is kind of a trick that you can use, and still you're able to use these composite Simpson's rules. Now you can combine those. It makes sense to combine both of those methods because they have the same order of accuracy. And that will be detailed in the final section of this video lecture. Let's apply the Simpson's rules or the composite Simpson's rules to this decelerating airplane example, where we also investigated this already for the rectangle and the trapezoid rules. And I just already show you the results here. So some side notes that I have to make here, well, for rectangle and trapezoid, we could always say we just simply pick a simple amount of subintervals and it should work. For these Simpson rules, well, if you only want to apply such a Simpson 1/3 rule, the amount of subintervals had to be even. So here I had to use 2 subintervals instead of 1. For the Simpson 3/8 rule, well, the amount of subintervals has to be divisible by 3. So here I use 3, and then here I use 9, here 99, etc. So that's a small side note, but it doesn't really affect the conclusions that we have here in a lot. Because what I want to show you here is that even for only 2 and 3 subintervals, so that is basically the standard basic, well, the most basic form of Simpson 1/3 and Simpson 3/8, we are already quite close to the rounded value for this exact value of the definite integral. So this is already much more accurate than trapezoid, midpoint, or rectangle rules. And indeed for the Simpson 3/8 rule, well, even only using here 3 function evaluations, we are about as close, well, we're actually much closer to the exact value than we were for both left and right triangle for 100,000 function evaluation. So this really indicates that such a Simpson method is extremely much more accurate than these rectangle methods. Also, when adding more subintervals, we see that we immediately attain at least up until 4 digits accuracy, we immediately attain something which corresponds to the exact value over here. And again, later on, we will do a bit more detailed error analysis and look at what actually happens after these first 4 decimal digits. But for now, the conclusion here can be that the Simpson methods are extremely much more accurate than rectangle methods, and they're also quite a lot more accurate than the midpoint and trapezoid methods. And why that is will also be discussed later on in this video lecture.